So prove that this new definition makes sense if z is a real number. You might want to pause the video and actually attempt these three problems before watching the solution that I'm about to present, and they're going to mirror very much the ones that we just did for cosine. So e to the iz minus e to the minus iz over 2I. That's equal to cosine of z plus I sine z minus cosine of negative z plus I sine negative z. And that's under the assumption that z is a real number divided by 2I. Okay, now what happens? Cosine z minus cosine of negative z, those cancel because cosine is an even function. Sine of z, here I have sine of negative z, but the negative cancels the negative that pops out. So this is equal to I sine z plus another I sine z, using the odd property of sine for real numbers, divided by 2I. So we get 2I times the sine of z divided by 2I, which is just the sine of z. So in short, this works if z is a real number, and so we'll extend the definition in the case that z is a complex number. Okay, second, let's solve sine of z is equal to 0. So let's solve e to the iz minus e to the minus iz over 2I equals 0. That implies that e to the iz must be equal to e to the negative iz, which is the same thing as 1 over e to the iz. So multiplying up, we get that 2e to the iz, e to the 2iz is equal to 1, which is e to the 0. And so therefore, these two, e to the something equals e to the something else. That means that the two somethings, e to the iz, have to be the same, though they may differ by a multiple of 2 pi I, 2 pi ki. And so dividing by 2I, that gives that z, where k is a real number, or k is an integer, pardon me. So dividing by z, we get that z must be equal to pi times k, a multiple of pi, where k is an integer. And so we already knew that sine of x equals 0. The graph of sine of x crosses the x-axis at the multiples of pi. And this proves that there are no complex numbers where sine of z equals 0 other than the ones that we already knew. We conclude this discussion about solving sine of z is equal to 2 in the complex plane. As with the case of cosine, this is patently impossible if z is a real number, but this is possible if z is permitted to be a complex number. So let's start solving. E to the iz minus e to the negative iz divided by 2I equals 2. So that gives us e to the iz minus e to the minus iz is equal to 4I. Now we'll make the substitution. W is equal to e to the iz, so that when I take reciprocals, 1 over w is equal to e to the negative iz. And so we get w minus 1 minus w is equal to 4I. Or if we combine everything on the left-hand side and clear out the denominator, we get 4w squared minus 4iw minus 1 is equal to 0. So applying the quadratic formula, we get that w is equal to 4i negative b plus or minus square root of b squared. Negative 4i squared is negative 16. Then minus 4ac, minus 4 times 1 times negative 1 gives a plus 4, divided by 2a. So this becomes 4i plus or minus the square root of negative 12, and the square root of negative 12 is 2i square root of 3, divided by 2, which is I times 2 plus or minus the square root of 3. And so remember that w is equal to e to the I z. And on the right-hand side, we have 2 plus or minus the square root of 3 times e to the I pi over 2. So therefore, to make everything match up, let's write 2 plus or minus square root of 3 as, do on the next line, e to the I z is equal to e to the natural log of 2 plus or minus the square root of 3 times plus I pi over 2. And so we match up the exponents. I times z is equal to the natural log of 2 plus or minus the square root of 3 plus I pi over 2 plus 2 pi in. 2 pi n times I, where n is an integer. And so dividing by I, we get the final solution that z is equal to negative I times the natural log of either 2 plus square root of 3 or 2 minus square root of 3. So there's two sets of solutions, plus pi over 2 plus 2 pi n, where n is an integer. And so we have this infinite number of solutions to the somewhat strange-looking equation sine of z is equal to 2. We have this infinite set of solutions if the numbers are permitted to be complex. Now, to show that this actually does work, let me use the calculator to justify this. So let's put in negative I times the natural logarithm of 2 plus the square root of 3 plus pi over 2. And let's store that into the variable z. So that's whatever that complex number is. Now let's go ahead and compute the sine functions. So let's compute e exponential of I times z minus exponential of negative I times z, close the numerator, and then we divide by 2 times I. And let's see what comes out. And 2 comes out, not surprisingly. So that's the plus case, and I'll leave it for you to check with the calculator that the minus case provides the exact same thing. So that is the solution of this equation, sine of z is equal to 2.